For our fifth presentation, I would like to call upon, we have actually two speakers. So let me introduce you to Advait Gokhale first, who is a delivery manager at Equilibrium Solutions Private Limited with 16 years of work experience. His CA experience mainly included ICEs, EVs, underhood and vehicle thermal management, cabin and vehicle interiors. He holds a master's degree in design engineering from Pune University. And then let me introduce you to Arun Rony, who is a senior CA engineer at Equilibrium Solutions with responsibilities in 1D simulation, e-motor design and simulations, as well as CA customization and automation. He has experience supporting global and Indian OEMs with simulations in topics of thermal management, cabin comfort, motor design and vehicle system. I welcome both Advait and Arun on stage to talk about methodology development for virtual performance evaluation. This time we are going on a three-wheeler ride again, but this time through busy streets of India. So welcome.
Can you hear me? Perfect. Okay, so good afternoon, and thank you to GT team for this opportunity to present at the conference at India level. So myself, Advait Gokhale. So we are here to talk about mainly the methodology development for a three-wheeler BEV. So we have seen a lot of presentations, also a three-wheeler presentation, which was really good, and most of the topics were pertaining to some cases or some components. And here what we are talking about is mainly regarding the complete methodology development at the initial stage of the product development, where you have to select your battery, the motor, the other accessories, and predict where your vehicle will satisfy the driveline conditions or will be able to undergo the expected performance or not. So that is the whole idea of going for this presentation, where we'll be discussing about some important steps in this methodology. So we will be going for some component level modeling and calibration and using those components into a system level model. As since morning we have also seen the system level is the way we are going forward. Initially it was a component level development which has turned to the system level development these days. So that taking into mind, we are focusing more on the system level performance here. Going further, first I'll take this opportunity to introduce Equilibrium Solutions Private Limited. So we are an engineering partner for global customers, and with the vision of developing ourselves as the CA Center of Excellence. We come with the rich experience of more than 16 years and with the complete portfolio in the automotive engineering, complete from component level to the system level. We have a team of highly skilled 120 plus CA engineers working at our office, and with all the in-house HPC capabilities and all the industry standard requirements. We also have the good certification for the ISO and TISAX, which are required in the market. With the kind permission, we are able to show some of our global esteemed customer names here. I'll also like to thank GT. So now we are also a GT, one of the GT's support companies. We have registered recently, and we are expanding into this GT system level simulations quite a lot. So from here onward, the technical part I'll give to Arun to explain to you, and we'll be available for questions afterwards again. Thank you.
Good afternoon, everyone. Thank you, Mr. Advait, for that introduction. We'll start by looking at what motivated us in choosing this topic today. Here we are starting from the electric three-wheeler market growth rate for the year 2020-2025. As we can see, the market is highly fragmented, and most of it is concentrated in the Asia-Pacific region, and is often referred to as an emerging market for electric three-wheelers. And some of the reasons for this change that we talked about is owing to the low end ownership cost and the government aid. One instance that can be noted here would be the FAME India scheme, which aims to subsidize electric three-wheelers and electric buses. And lastly, one point would be the decrease in battery cost. These are some of the reasons which drove us in choice of this topic here. Before we move into the main topic, let's start by looking at the general electric vehicle design stages. It begins all from the conceptual stage by understanding the vehicle requirements. These includes vehicle parameters such as the range, the speed, and the torque to be attained. And from there, we will develop a system level model for a feasibility study. After the feasibility study, we will go on for further design and optimization. Now, once we have the outer shell of the vehicle body, we will go for a space model development. This helps us to analyze different vehicle shapes and the floor configurations. This is followed by a packaging analysis of the parametric CAD model. And the space models are further examined using topological optimization on the global load paths. From these set analysis, we will be able to develop the body in BIW. That would be our first stage. Then at the component level, we have the traction motor. We are starting with traction motor. And for any design of motor, we start from the initial specifications. That's the torque, speed, and the dimensions, size restrictions. From these, we will be able to develop an analytical model, which will be further optimized based on the winding architecture and the topology. And then they will be subjected to the target drive cycle evaluations. And from there, we will develop the most optimized motor design. Then that will be taken for further advanced electromagnetic simulation, multi-physics optimization, and then integration to system level. Now we are moving on to the next important component, that's a battery. And at times, it's the most important and expensive component which powers the entire electric vehicle. Here also, we will take in the basic size constraints, and then we go into the modeling of the battery. So that can be broadly classified into 3 stages, starting at the cell level where we choose the cell chemistry, the cell type, and then into the pack level, which we study more about thermal management of the battery pack. And then finally, taking the optimized model into system level to see the performance of the battery pack at various operating points. Finally, we have the power electronics, which basically includes the converters, inverters, and onboard chargers. They typically operate high frequencies, high voltage and high current, so that leads to high switching rates. This translates to high thermal responses, calling for thermal management of power electronic devices. So these are some of the components and the overall stages which are involved in battery electric vehicle. So the key takeaway here is this a multi-physics phenomena, as we saw, and it calls for integrated engineering approach. So we need to evaluate them both at the component level and also at the system level. So now we are moving into the objective of the current study. So here we are trying to define the methodology to develop the three-wheeler in GT suite and to evaluate. So it has been basically done in 2 stages. One at the component level, where we'll be validating the individual components and then taking into and defining the models in GT and further taking into system level. And then finally, we'll see the performance of the system as a whole. So first we'll start from the component level simulation. So we are starting from the traction motor, and we are validating this with respect to some test data. So from there, we have got the winding parameters, our material definitions, as well as the geometric inputs. With this, we will be able to develop the analytical model, and from that, we develop a more detailed finite element for evaluating the flux distribution of the motor. This again was validated as the test results. Now, once we have this validated motor model from our electromagnetic solver, we will be able to take it to GT. Here, GT offers us 2 methods to model it. One is the equivalent motor method, and another based on the efficiency map. So these are some of the outputs of interest that we got from our electromagnetic solver once we model the motor. On the top, we have the efficiency versus speed curve, the torque per speed curve on the right, and at the bottom, we have the current per speed curve. We can observe some high current at the starting. This is owing to some structural characteristics of the motor. And similarly, owing to the high drive force in the beginning, we are seeing high torque at the beginning. And with respect to correlation, we are able to see less than 10% deviation with respect to test results. Now moving on to our next component, which is a battery. Again, here GT again offers us 2 methodology. One is a detailed electrochemical modeling with the help of auto-ion, and second, an equivalent circuit-based approach, which takes in 2 key primary inputs. One is the internal resistance for charging discharge curves and open circuits curve for charge and discharge cycle. So below we can see a typical equivalent circuit for a battery model. On to the right, we can see how these input curves have been fed into GT. On the top, we have the SOC versus time curve for open circuit voltage internal resistance. These are the characteristics input curves which are fed into the model. And here we have considered a lithium iron phosphate cell, a prismatic cell for our evaluation. And we can see the test result with the SOC versus time. and the correlation with test results for the performance of the system, for the system load under the transition simulation. So we have seen how we have modeled the electric motor and the battery pack in GT and how we are calibrated with respect to the test results. And now we move on to see how to take these components into the system level. Let's start from the system level by looking at the specifications of the vehicle. So here we have considered a commercial three-wheeler vehicle based on the available data, and throughout the entirety of the simulation we have taken the 3 passengers, 1 driver and a payload. And on to the right we can see some of the key characteristics of our vehicle that we have considered. Next, we are talking about specifications of the components that we have validated earlier that has been taken into the system level. So starting from the motor side, we had considered 3 kilowatt motor with a rated speed of 1600 rpm and having a torque of 20 Newton meter. As discussed earlier, we have considered efficiency map based model. So here it is a contour plot of torque, speed and efficiency points. This is what being fed into GT as a lookup sheet, and GT will interpret the results from using this. On the right, the battery pack we have considered is a lithium iron phosphate prismatic cell, which we discussed earlier. And for a range of 60 kilometers, we have considered 15 cells in series and 4 cells in parallel, having a rated discharge of 1C. So these are the components that we have considered for a system level analysis. Now let's look at the 1D map workflow in detail. In the middle, we have the vehicle body component, which calculates the longitudinal motion of the vehicle. And then onto the top, left, right, we have the electric motor model, which is based on the efficiency map. So that takes in the brake torque and the power as input to give out the torque speed with respect to efficiency map points. This is being connected to the differential in the middle that we can see. That splits the obtained torque into the left and the right wheel. The axle component considered here is actually rotational inertia, so any compliance and damping is being ignored here. The tire component basically computes the traction and the rolling resistance. And from here, the gross tractive force and the normal load on the vehicle and the axle based on these tractive characteristics will be computed. And then onto the top right, we have the driver model, which takes the vehicle speed from the vehicle body component and the motor speed as its 2 inputs to give out the required wheel brake torque for the vehicle acceleration. It's like basically a feed-forward component that has a PI module also inbuilt that minimizes the error between the demand and the instantaneous values that are coming in. And finally at the bottom we have the road component, which takes into effect the road grade and the road curvature into the simulation. So those are some of the key components involved in the vehicle 1D map model. And here we have considered a very primitive battery controller which aims to limit the battery power to avoid overcharge and discharge. So this is a primitive battery controller that we have modeled for initial analysis. Now moving on to the loading scenario, we have considered the IDC cycle. So, and GT provides us a default cycle that we can be taken, and some characteristics of cycles are onto the right that we can see. And we are given a starting battery SOC of 80%. And the IDC is typically a cycle of 6 segments of 108 seconds in duration, so we have considered 1 cycle of that. And these are some of the outputs of the 1D system simulation. On the top, we have the gross tractive force that have been computed, and it can be observed that the main force that needs to be overcome is the linear acceleration forces. On the bottom, we have the relation between the motor torque and the wheel torque based on the gear ratio that we are given. Next would be the effectiveness of the system. We can see how it is effectively tracing the actual demand and the request brake power. And also GT will be able to give you out the energy consumption for the range that we have specified for 91 cycles of the IDC. So that we can see the energy demand prediction for also from the output. Moving ahead to some of the conclusions. We can get an easily configurable model that we can scale up or down. And also we can consider multiple DOIs and to see the various performance of individual components also. In GTS, again, when we talk about GT 1D map models, it offers us a quick and easy configurable models. And we can do better sizing performance easily and at a reduced time. Also, it helps us to evaluate multiple DOIs and their performance criteria. And eventually, all these translates to reduce physical test costs. And some of the assumptions in our early initial system model are that we are not concerned thermal dependencies of the multiple components that are involved, and a very primitive control strategy was adopted in the early stage. And most of vehicle parameters were based on some commercial vehicle data. So now moving on to the future scope of our study, we would like to validate the parameters that we consider for equivalent circuit model using the characterization tool for the battery, as we've seen in some of the early slides. And then we need to validate our system level model with actual test data to confirm the adherence to the test results, and to bring in a more detailed inverter circuit into the study. Then right now we have not considered a detailed inverter circuit, only the inbuilt GT options, which takes in only the efficiency. So more detailed circuit will be part of the interest in the future study, and a better energy management strategy with the help of ultra supercapacitor, which will be in conjunction with the battery, to offer in more higher power density and some other benefits of ultracapacitors in conjunction with system level modeling. Then finally, we would like to evaluate the tested model, system level model with the actual traffic data to evaluate the performance of the C-rickshaw using GT real drive. Thank you.
Thank you, Advait and Arun, for a great presentation.